Welcome to Superposition method for hot rod. PET 690, well completion and intervention. We look at an example from the 6th edition of the undergraduate textbook Mechanics of Materials. This example is the same as in the original book by Beer and Johnson many decades ago. This is a classical application of the superposition method. Picture A, top. Consider a steel rod at rest on a frictionless table. The length of the rod is L. Picture B, bottom. Now, heat the rod and observe it expands. Thermal elongation is easily calculated from thermal expansion coefficient, temperature change, and initial length as shown by the equation. We now look at the same rod, but at this time the rod is fixed on both ends. This is the question on hand. What is the compression in the rod after heating? In picture A top, we see the rod being heated while constrained by fixture on each end. There is no longer any thermal expansion as in the previous case. Instead, the temperature increase gives thermal stress and strain. Picture B bottom shows our unknown force P, used in the method of superposition. We let the rod expand freely and then we push it back to its original fixture points using this force. This is the force needed to bring the rod back to its original length after heating. The thermal strain is a product of the thermal expansion coefficient and the temperature change. There are two easy steps in the superposition method. 1. Free expansion of rod. 2. Push rod back. First, we calculate thermal elongation during free expansion. Second, we use Hooke's law to express mechanical contraction as we push back. Finally, we combine these two equations to give our desired solution in terms of force P. The total deformation, elongation during heating and contraction during pushback, must be zero since the rod is constrained. Our desired solution is shown in the middle of the page. Dividing the force P by steel cross-sectional area A gives us axial stress sigma. This is the bottom equation. The negative sign means compression. The chief input parameter is the temperature change with a direct relation to axial stress. Young's modulus and thermal expansion coefficients are considered constants for a steel rod.